Okay. Hi, goedemiddag. Don't worry, my talk will be in English. I'm the Scala team lead at Typesafe. I've been hacking the Scala compiler since 2007 when I decided that all Scala needed was for world domination or higher kind of types. So you might call them higher order generics or type constructor polymorphism. That was kind of how I started out with Scala, and so I guess you can blame or thank me for that. Since then, I've kind of come to my senses, and in 2.10 I did the pattern matcher, for example. And so right now I'm leading the team at Typesafe. So I'm guessing you've heard Scala is this functional object-oriented programming language that we didn't talk about during the keynote for some reason, but that's okay. We're also a tool that aims to make you more productive, and we think our unification of functions and objects does just that, and that's the main goal for us. Under active development for over a decade, we just celebrated our teenage, the beginning of our teenage years, sorry, and growing pretty steadily, and yeah, I would say vibrant community. That's one of the things that we at Typesafe are actively working on, is to help the community work on Scala, get started with Scala. So we see ourselves as the stewards of the project. Not just because, you know, our not-so-secret sauce for the reactive platform is Scala, and so everything that we do is implemented in Scala. We do provide great Java 8 APIs, so you're welcome to use it from Java, but I think you'll have a little more fun doing it in Scala. So quickly about that community, when we look back at 2.10, which was about the time that I joined Typesafe and left EPFL, the community had about 10% of the commit pie that you see up there, and 2.10 was a pretty massive release with a lot of features that I won't go into today. And then the split between EPFL was and Typesafe was about 50-50. So in 2.11, we focused on stabilization and modularization. So that's why the absolute size of the pie got a lot smaller, but the relative size of the community's contributions tripled. So very proud of that, very thankful for that. And EPFL is as well, so those students can now focus on their dissertations and writing papers and doing more research. And so we're still about 50% of the work. We try to do the more boring stuff. So similarly, another metric that I kind of made up is what's the core team size, and I just defined that as who is doing 90% of the work. So who's doing repeated, who's sending us repeated pull requests. So a handful of people both at EPFL and Typesafe. So we're not a big army of Scala compiler hackers or anything like that. But there is a pretty big army out there. Stood at 33 regular committers, and it grew by quite a bit in 2.11, and one of our goals at Typesafe is to keep this growth going, and yeah, so thank you very much for that. No pressure, keep up the good work. If you have, yeah, thank you. I know getting started with Scala both as a contributor and as a user might not always almost be the easiest thing you do. I hope it will be the most fun you'll have with programming languages, but come talk to me if you have ideas about how we can simplify this, or things that kind of kept you from contributing, for example. I'd be happy to see what we can do there. So to the meat of the talk, I'll be talking about 2.12, and it's easy to summarize Java 8. We're very excited about having all those features available to us as well. We've been jumping through a lot of hoops over the years to compile functions to the JVM, to compile traits to the JVM, and those hoops just got a bit wider and less fiery. So that's pretty great. So I'll talk a bit about the nitty-gritty later. So one of the things that I did want to touch on is that I know a lot of people are still in Java 6 and are planning to be on Java 6 for quite a while longer. Oh, that's not a problem. We do intend to publicly maintain 2.11 well past the Java 7 public end of life. And if you need commercial support beyond that, just give us a call. But to make it easier to switch back and forth between 2.11 and 2.12, they'll match features as closely as possible, of course, with Java 6 being the common denominator. So a little bit about what you can expect from the rest of the talk. So I'm going to start off by ranting a little bit about functional programming. I'll give you definitions and make some controversial statements and see if I can keep you awake and from running away to lunch. I can't really see you, so if you're too hungry, that's okay. So then I'll show you how to use Java 8 APIs. So for example, the streams, which we're pretty excited about. How to use them from a Scala REPL, which is a great way to experiment. I hear that that's coming to Java at some point. And of course, vice versa is equally important, so I'll talk about that as well. And then at the end of the talk, I'll give you a bit more insight into what kind of bytecode we generate. And the gist of it is, if you get too hungry by then, Java C8 style bytecode is what you can expect from the 2.12 compiler, as well as from the 2.11 compiler if you're running under the Java 8 experimental flag. So what is functional programming? What is that all about? Why is everybody getting so excited, or why is this such a controversy? Well, we just call it programming in Scala, really, and that's roughly all I have to say about that. I mean, as we all know, programming is about dividing into abstractions of the right size and then composing them back together without losing any safety. You want to be able to factor out common patterns and then later use those all over your code rather than duplicating them and have slightly different bugs in every instance of that duplicate. So, and our claim is that very often functions are the right size, and I'm very happy that I don't have to really go into too much detail, because that was basically what the keynote was about, or at least the first part. So very often this kind of behavior, if you want to react to an event or you want to do something to every element of a collection, you want to do stuff in parallel, you have a ton of data and a little bit of code, so why don't you just ship the code to the data instead of the other way around? All of these are examples of what functions are good for. Now, if you need a bigger abstraction, we got you covered with that as well, of course. So we got traits and objects, and at heart, Scala is an object-oriented programming language. So now onto my definitions to really get the fiery debate going. So in my definition, OO is programming with objects, and I'm not trying to be facetious or something. I mean, objects are your values. That's the key thing that you think about. And from that, it follows that you have a closed set of methods. You tend to think of, that's what I have for my object, and you want to define new subclasses and new subtypes, because that's kind of the problems that we deal with most often in modeling and simulation, which is where OO has its origins. And, surprisingly, functional programming is programming with functions, and you kind of swap the expression problem around, because that's what it tends to be called in the computer science literature. Now you get extensibility of your functionality for free, but it's harder to get to insert new types in your system. So commonly you don't have subtyping in functional programming languages, which allow you to do stuff like that. So then there's a whole other bunch of labels that people like to apply, either specifically to OO or to functional programming, and I tend to disagree. I tend to think that all of those labels apply to both OO and functional programming languages. There's no reason you can't have an object-oriented language that's pure. I mean, it might take a lot more typing in Java, but you'll get there. And the same thing holds for laziness and strictness. Scala is not a lazy language, but I think it's perfectly suited as a functional programming language. And I'm not even going to talk about static and dynamic typing, and I'd rather not talk about math. All I'm going to say is that I think math makes you a better OO programmer as well as a functional programmer. In Scala, we think there's no need at all to go deep in math to be productive. Scala is a tool. Functions are a great abstraction. If you want to talk about monads, there's other talks. I'm not going to go into that too much. We like to hide them away. So to capture the essence of what I've been saying before is that we think of functional programming as object-oriented programming in the small. And if you want to make a recursive definition here, you could say an object is a bundle of functions, and that's how programming language theorists model objects, or used to model objects. They just took a bunch of lambdas, abstract over themselves, and so on. And you can implement late binding and all that pretty easily. But a function is actually just an object with one method, and that's what we see now in Java 8. That's a very convenient encoding, and that's what we've been doing in Scala for the last decade. We call that method the apply method, and you can omit that apply name when you call a function, which is just an object on which you can call that apply method. So in that sense, Scala doesn't bolt on functional programming onto an object-oriented language. It's a nice unification. And like I said before, functions are often the right abstraction. They're what really captures what's different between different parts of your code. And a very nice property of functions, and combined with purity, is that they're easy to understand. They're very often, the amount of code that you can keep in your head, and you just need to know what's coming in through the arguments to understand what's going out. You don't need to think too much about mutable state that's shared. That's the devil's work, as a wise man said a couple days ago. And that only holds if those functions are pure. And so purity is usually a good idea. I'm going to go too much into this, but, I have to say reactive at least once. And, that's what my contract says, sorry. So the reactive programming paradigm and everything related to that really is built on this idea that you have units of behavior that you can distribute over a cluster or cores on your computer or threads or, whatever. I don't think it needs anything more for motivation. So Scala is a very pragmatic language in this sense. It doesn't force purity on you. It just gives you a little nudges once in a while saying, hey, why don't you type file here? It's just as many letters. So let's take a minute to just look at some contrived code that I fit on a slide here. And on the left is what you might write when you like mutation a lot. And so you want to compute some local variable. So you make it mutable, you set it, you don't initialize it, or you do in this case. You check some expensive condition and you compute an interesting result, and then you return it maybe after doing some post-processing or something. So really what you want to know at the end of this block here is what is the value of x, and you need to know what the dots are in order to answer that question. Now when you go to the right side, which is where Scala wants you to be, you just look at how val x is defined, and that's all you need to know. So a couple of things to kind of snarkily note. If is an expression in Scala, so we don't need a ternary operator. So get that, we have one fewer operator compared to Java, at least for this one. And I think that's all I wanted to say about that slide. So I think that the take-home message here is statements cause side effects, and that's why we don't have them. It's an expression-based language. And to me, that's one of the key things about pure functional programming, is that you want to focus on expressions. Statements, they push you towards mutation, and once you start sharing or seeing that mutation across different parts of your program, you're into trouble. So like I said, Scala is pragmatic. Mutation is a side effect, just like, let's say, checked exceptions. The compiler doesn't bother you with either of those. So if you feel like mutation makes sense in a certain piece of code, so let's say you have some kind of profiling counter and you want to increment it every time this lambda gets called, hey, just go for it. The IDE will show you those variables in red, but that's the extent we'll go to nudge you to purity. So to conclude this kind of, what I think functional programming is like, and what we want it to be like for you when you're programming in Scala, is it's not that controversial. And so when people say stuff like that, everybody is like, what? Is it time for lunch already? Like, yeah, sure. And so, but when you say stuff like this, everybody's like, higher order functions, combinators, composition, what? But it's really just the same thing. If you think back to our definition before, you can think of objects as just a bundle of functions. So when a method takes an object, it's actually abstracting over functions. So it's a function abstracting over functions. That's a higher order function. That's all that means. So when a function takes a function, like map taking whatever transformation you want to apply to all the elements of your collection, that's what we mean. And so, by the way, Scala does that on the type level as well. That's what I mentioned earlier. To convince you I know what I'm talking about, it has higher kind of types, which are basically type parameters that abstract over type parameters, and they're pretty handy when you're defining library abstractions like the collections. But I'm not going to talk about that today. So to give you a couple of examples, what function composition does for you. Ripping out iteration is an obvious one to everybody. Abstracting over nulls now with optional in Java 8 or option in Scala. And an extension or generalization of that is validation, which I think is a very nice pattern where, let's embrace failure and let's be able to tell your users what the failure really resulted from. So by expressing your computation that might fail as a set of functions, you have a handle on that failure and you can tell what's going wrong. And the same pattern comes back over and over again. And my favorite one is the Scala Async project, which lets you work with futures in a delimited scope. And in that scope, the macro, in this case, will get a handle of all your future computations and run them off in parallel, and you don't really have to know that any of that is going on. So, as we like to say, you just flat map that shit, and that's function composition for you. Really quickly, something about high-tech plumbing, and I don't have a nice graphic like the keynote today, but that's kind of what I was thinking of. Types guide your values in the right destinations, and if you've been to any of the reactive streams talks earlier this week, that's really what I'm talking about, is you look at the signatures of your transformations and you know what they're going to do. So once you ship them off to your data center, you don't have to wait for it to run for a couple hours and see if you shoveled all your ints into int buckets and all your strings into the string buckets. But I guess that's kind of obvious if you're coming to a Scala talk, so I'm not going to spend too much more time on that. So that doesn't mean that you shouldn't test, obviously, and the type system, at least in Scala, doesn't have that ambition. We're not a proof assistant. We don't want to make the type system so rich that you can just say, well, it compiles, let's go home. And finally, and that's, I think, the most important point is when we're, implicitly this is, of course, a competition with Java 8. So, I would claim our type inference makes your lives a lot easier when you're programming in Scala. And you could say, sure, my IDE, fills in all the blanks for me, and maybe that solves your problem. But now, actually, you have two. You have to maintain all that boilerplate, and when you refactor, the IDE won't regenerate that boilerplate for you. It's there. It's the same problem as when you generate getters and setters and so on. So in Scala, we have pretty powerful local type inference. What that means is that it operates within methods, not interprocedural, excuse me, like other functional programming languages, because we believe that public type signatures are your contracts, are your documentation, and no one wants to infer Java doc. Right? I mean, maybe it'd be better in some projects, but I don't recommend not having your return types inferred, even though in principle we will do that for you. So to quickly recap, the key thing here is that a function is a value and it lives on the same first-class citizen status as all the other values in your language. So you have a nice way of expressing literal functions. You can pass them around, you can abstract over them. And because pure programs are easier to reason about, Scala nudges you towards that by thinking in terms of expressions. You don't want the side effects that are caused by statements. Very often they don't help in program understanding. And like I just said, both types and monads are things that we want to have, to be working for you behind the scenes. It's great for library implementers to have a rich type system and to think in terms of very abstract concepts, because that's what you're doing. You're trying to capture a lot of different patterns in terms of categories or other mathematical ideas. And that's a great vocabulary to have when you're working on those kind of libraries, but we really try to hide that from the user. So our for comprehensions, for example, are expressed in terms of for each and flat map and so on. But they don't have to be a monad for the for comprehensions to hide the ugliness for you. And my personal favorite, pattern matching, but unfortunately I won't have time to talk about that today. So let's get to really where Java 8 and 2.12 meet. And I'll give you an example of what you shouldn't be doing with SAM types, much more easily spawning new threads yourself. But I guess you can kind of see what the syntax looks like, or the syntax savings. And I really like the way that they introduced function types, at least from the operational perspective, on the JVM. And so we're implementing feature parity so you can easily use SAM-based higher order methods from Scala. So I'm honestly not brave enough to do live coding in an audience like this. But I figured the next best thing is to just have Keynote type everything real quickly. So in a recent 2.11.5 snapshot, I had to fix a couple bugs while I was writing my talk. We get experimental support for SAM types, and so I just Googled Java 8 streams tutorial, and I took the first hit, and I started coding away in the Scala REPL. So this is a great way to get to learn Scala. I mean, we have other great ways like Activator or the worksheet in Eclipse, and the same thing with IntelliJ. But I'm more of a console guy, so I like to type in the REPL. So let's just get started with importing a couple things that are pretty. You've seen lots of times by now. And the key thing, I guess, to reiterate here is that the type for the local variable mylist here is inferred. You don't need to write it. So that was the first fragment in that blog, and the code is linked there in the bottom. It looks exactly the same, except we have fat arrows instead of the more, health-conscious version that they have in Java. We have the wunderbar already because we had the foresight to never allow it as an identifier, but I hear in Java 10 you will get it as well. So get rid of those underscore identifiers. I mean, who does that? Does anyone have that in their code? So the underscore dot to uppercase is basically the same as S to S dot to uppercase because it's such a common pattern. And we didn't want to introduce things like syntax for method handles or stuff like that. So we kind of give you a very succinct way to do essentially ETA expansion. And that's what the print line at the end there is. It's just a reference to a method, and when the Scala compiler sees there's a method in a position that expects a function, the method isn't applied to arguments. It'll just apply to arguments and put that in a function. By the way, if anything I says doesn't make sense, you need to yell pretty hard because I might not hear you at first, but I'm happy to take questions during the talk as well as after. So as another example, in this one, I removed the dots because I felt like it, and that's one of the key challenges I believe in Scala is that you need to develop your own style. We let you decide whether you want dots or spaces. And there's tools to help you with defining and nailing down automatically what your code style should be, but ultimately it's up to you. And I believe that's a lot of where the Scala is complicated. Criticism is coming from is that we have fewer restrictions. That's right. And I believe that those restrictions, they should come from separate tools like your IDE, like your in-house style guide, and so on, not from the language. No, that is not to say that we will remove ideas that didn't work out, and that's what we're doing in Scala. We deprecate things, and they will go away if it turns out it wasn't a great idea. In this case, though, I think this is pretty neat. And one other thing I wanted to point out is that we added string interpolation, like the argument to print line there. That's actually completely user extensible. So other libraries, I/O libraries have URL interpolators, or our macro mechanism has a quasi-quote interpolator. Have a look at string context, and the S actually is a method that's called on string context, and this thing is expanded in a very regular way so that you can use those interpolated strings both in patterns and in value positions. So I really, it's kind of my favorite feature of 2.10. It's probably not the most celebrated one, but maybe that's why I like it. So behind the scenes, the Scala compiler does exactly the same thing as the Java compiler in this case. So when you look at the same expression that I had before, that actually wasn't type correct and isn't type correct in 2.11 if you don't specify the experimental flag, because we're expecting a predicate and we were passing in the Scala case, a function 1. I'll talk a bit more about our function hierarchy later, but suffice it to say now that the compiler now knows to say, well, I have a function literal and I'm expected to produce a predicate. I know exactly how to do that. And so I'm assuming that you've seen this in Java talks before. It's pretty straightforward. I guess we lift the body out to a method that's defined in the same scope as the original closure, and then we create an anonymous subclass of the SAM class that's the target type of our expression. So I just want to, I don't know, I couldn't help it. I wanted to put the other side of the equation on the slide as well. And that's what you see, of course, when you're implementing map on stream. And that's what the guys in Oracle are doing, right? Or the community in OpenJDK is the signature up there. So I guess I'm biased, but I like shorter signatures, and I'm going to explain to you why these are exactly the same, and I'll break down the Scala one for you step by step to convince you of that. Now, I mean, full disclosure, when you go to our collection library, there's a lot more magic going on in the signatures with implicit search that I'm not a great fan of personally. But they give you the nice property in the Scala collections, as a little aside, that when you start with a set, you end up with a set, except if you're mapping something that's not a set. So that's a whole other design discussion, but let's just take the translation of what we have on stream right now and compare it to what you would write in Scala. So that fat arrow is actually just a type alias for function 1 in this case. So that's a simple expansion right there. Now you can write types both in fix and in the classic style, and it means exactly the same thing. So is that jump clear to everybody? Now let's focus on the types, right? And I just quickly want to talk about use site variants as opposed to definition site variants. So in Java, you have to say that I take any function of an argument type that's upper bounded by t, and then I return you some type that's, sorry, that's the argument is, see, I get it wrong every time. So the argument type is in a contravariant position, so it's lower bounded by t. The result type is in a covariant position, so it is upper bounded by r. So you get some subtype of r as your result from your function. In Scala, we write that exactly the same way as function 1 of t and r, because that's what function is defined as. We have those little variants annotations that use minus for contravariance and plus for covariance. And really what that means is it's kind of like a bound on your type parameter and saying instead of what this type parameter needs to, this type argument needs to comply to, it says this is an abstraction that takes a t here, and I promise you I will never use this t outside of contravariant position. So in other words, in this case, I will use this t only as the argument type of methods or other contravariant positions. But in this case, it'll be the argument type for your apply method. And similarly for R, the compiler checks that you use that R only in positions that make it safe. And so in this case, a covariant parameter type parameter needs to occur in, let's say, the result type of your method. And what that means is that you can compare a function of any to string to a function of int to string and decide which way the subtyping relation goes. So in this case, a function of any to string is a subtype of a function from int to string. Because of the contravariance, you flip the subtyping for the first type argument. That's why it's a negative thing. It goes the opposite way of the subtyping of the applied type constructor. Now, you can encode that if you're diligent, and in every use site, you just declare function as an invariant one, so the compiler doesn't check anything about where the t and the r occurs in your code. But that means that you need to be very careful if you want to have the same kind of subtyping relationship. So the map function will require something like that. So you better make sure that you have something that has similarly bounded wildcards. Can I get a sense of like maybe some grunting if this is really unclear or just too obvious? Dead silence. Okay, so that can still mean two things. Maybe we can take it in questions later. But my point is that in Scala, we put the burden on the person who defines the abstraction, and the compiler actually takes away the burden and says, well, you say this is a covariant type parameter, I will make sure you only use it in covariant positions, you don't worry about a thing. And then later you get your users of your library not to have to worry about wildcards. And in fact, that's one of the rough edges right now in experimenting with SAMs, is that our wildcard inference isn't as good because it doesn't have to be. You only deal with normally applied type constructors in this case, and the subtyping just falls out because of the definition side variance. And even as a designer of the abstractions, most people get away not knowing variance, including myself, because the compiler will tell you when you use it in the wrong position. In my opinion, that's a lot easier to deal with than both having those wildcards and kind of having split interfaces depending on how you instantiate their classes. And I mean instantiate in terms of applying type arguments to their type constructors. So as another last snippet that I stole from that tutorial is let's suppose you have some legacy code that has kind of sets up a dangerous path towards foo that you really want to know, and on your way to that destiny lie null pointer exceptions, and you want to do the functional thing and encapsulate those null checks as going into the option monad. But really what that just means is, let's make an option of the outer thing, flat map, which does nothing if there was nothing there to begin with, and otherwise applies the function that I supplied in there, and creates another option. So that means that the O in the first line there is bound to the outer always, because new outer can't be null, so you'll have a sum of some instance there. And the O on the next line of flat map will be bound to that instance, and you can select O.nested safely and keep going in the option monad, essentially. So flat map is a kind of a combinator that has control over sequencing of computation in a sense. It can say, I'm done by returning none, or it can say, I want to go on and giving you the result that it wants to continue with. And eventually you safely reach your destination and you just print line it. How's that for a climax? So in Scala, we like I said, we tried to hide the monads, and so we have 4 comprehensions that desugar to roughly the same thing. So in this case, the for comprehension does the same thing. Again, it says, I want to bind O to whatever is in this option. Then I look inside the next one, and I keep that in the monad, and I just keep going. And if I'm successful and all the variables on my path, all the selections on my path return non-null results, I can print line the foo. And so the compiler will desugar that for you to the nested sequence of for eaches there. And it picks for each because that's slightly more efficient in this case, because all you're doing is side effecting at the end. You're not yielding a result. So otherwise you would use flat map for you. So that's one of the nice things about for comprehensions, is that your users really don't need to know that your library is monadic. In fact, I've said monad way too often already in this talk. So how about we turn to tables, and we, of course, want to be friendly to our Java consumers, because our reactive platform, let's say a Typesafe, is defined in Scala, but Java 8 is obviously an important market. So in 2.12, we just intend to make our good old function and interfaces functional interfaces, but on 2.11 we can't do that because there are multiple abstract methods in there. So we came up with a little compatibility layer that all it really does is guide the type inference in the Java compiler towards a SAM type that it knows how to instantiate. And that SAM type effectively is a subtype of the function n types. So to build that up, step by step, the first line there shows that you can assign the identity on strings to a J function one, which is defined in that GitHub repository that I linked there, and you get your F1. And to prove that J function one is indeed a subtype of Scala function one, we assign the variable in the obvious way. So this is just to kind of set the scene for how this works. So what's also in that package is something that you tend to statically import, the func overloaded thing, which is overloading all the arities that we support up to the magic 22 to guide the type inference towards saying, well, this is a SAM type that I know how to instantiate. So when you write func of that same identity function, the Java compiler will know what to do, and you can put that in a Scala function. And it'll even infer the argument types for you based on the expected type here in F4. So that compatibility layer is pretty simple. It just has a lot of overloads and a lot of different variations because you need to deal with unit returning, void returning procedures, which to us are just functions that return a unit. And here you're looking into the runtime realm, so it's actually a boxed unit because there is no such thing as unit, of course, on the JVM. But the idea there is that you're seeing a bunch of those func overloads that take a SAM type in their argument position, and they simply return it by upcasting it to a Scala function so that the types line up. And here is the real meat. Unfortunately, like I said, our Scala function ones have a lot of trait methods that are mixed in because that's our compilation scheme on Java 6 because there are no default methods. So you have the combinators like and, then, compose, and all their specialized variants. So JFunction1 implements them by delegating to the implementation class of the trait. I don't want to go too much into details of how our trait encoding works, but suffice it to say that we're trying to get rid of it and use default methods instead. So that's the plan for function n into 12, which will target Java 8. Excuse me. And here we really get down to the bytecode level, almost. I'm not going to show you bytecode, don't worry. We started in 2.11 with the first pragmatic step, and we said, how can we get as close as possible to what Java 8 will do while staying on Java 6? Because we just can't force our user base to move that fast. So what this phase does is it takes the body of a function and it lifts it out to a private method, just kind of like I showed you with the SAM translation earlier on the slides, but now for every function type. So that we're setting the scene exactly for what we need to use invoke dynamic and lambda meta factory on Java 8 and 2.12. And this is an instance of a general approach that we take in Scala is every big feature needs to be an experimental feature first for one release. And then when that works out well, we flip the switch and we let you use it by default, in this case in Scala 2.12. Even on Java 6, you get the nice benefit of getting smaller class files for your anonymous functions because all they are is just forwarders to the body that stays in the same site as where your closure is defined, so it reuses all the constant pool entries of that enclosing class rather than duplicating all of them because the body of the function needs to move to that anonymous class, to that class file for that anonymous function. Sorry. So more concretely, I cobbled together another nice natural example of something that we write every day, where we define a class that has a field, an immutable field. So that's syntax for primary constructors in Scala. So you can just do new C and give it a double, and it'll initialize that value C, and that's it. And then you can call that outer method with some argument that's captured by the lambda that it returns, as well as the C, which it will need to access through the dispointer of the C class in which it is defined. And so the result type of that outer is a function from int to double. So the lambdafy phase, what it does for you basically on 2.11 when you're not targeting Java 8, is it creates the same kind of class that we've seen before, which captures the environment at the point where the closure is defined. It extends the int to double function type, and it has the apply method, which is the single abstract method in our function interface, and that will forward to the body, which is a private method in the same spot as where in the same class that originally contained that closure definition. Okay, so now when we move to Java 8, we get access to the invoke dynamic instruction and the runtime support that goes with that. More specifically, the lambda factory meta, which Java C8 uses to translate its lambdas, and we'll very happily jump on that bandwagon as well and get all their engineers to work for us. So now there's no more anonymous class in there. Instead, we're asking Lambda Meta Factory to do a similar thing for us, we don't really care what it is, and hopefully every JDK version it'll get better. But what we're saying is we statically know, and that's what we're passing to the ind instruction, is that we want to bootstrap with lambda meta factory.meta. We're passing you the signature of the target SAM type and its method, which is a JFunction1 apply, because that's right now what we need to do to wrap these things into SAMs, and that's the only thing that lambda factory.meta knows how to instantiate. And then we give it the implementation. Then there's a second set of dynamic arguments that can vary in length, and that's the part that captures your environment. And so what the invoke dynamic instruction will do is the first time you reach this call site, it will bootstrap, and it'll spin up whatever is necessary to set the scene. And currently what it will do is spin up an inner class, just like we did statically in the compiler when we couldn't target Java 8. And then it'll instantiate that class to capture the lambda, and it'll return it, just like we did with the static code generated by Scala scene. And so yeah, so to kind of recap, because this is kind of mind-blowing, it happens in two phases, and this is a very interesting instruction, which you can think of as a macro for bytecode, right? And we're thinking of doing other things like lazy files and accessors with it. And this kind of just rehashes what I said. So there's two phases. The bootstrap happens only once, or until you unlink that call site, which we'll never do in this case. That's the one that creates the anonymous class that represents your SAM type. And then we instantiate that class to represent your function value. And that needs to capture the environment so that when the function is actually invoked later, it knows what all the values were that it needs to compute its result. And like I said, we can't really do that unless we move to Java 8. So this is actually the main piece of engineering work that we're doing now, and we're doing it first in 2.11 behind a flag, but the goal is of course to have this in 2.12, which will be out in 2016. We've taken Miguel Garcia, who was a postdoc at EPFL at the same time I was there. We've taken his backend and we're working on integrating and refactoring it so that it becomes ready for production. And I mean, it was already largely there, but it did need some more engineering love. So a lot of people wanted this sooner, but we're confident that we're going to get it into 2.11 as a nice experimental feature, and it'll be ready for sure to use as a default backend in 2.12. So the main thing is that it uses ASM. We used to have our own intermediate representation, and the optimizer operated on that, and we used to have a .NET backend and so on. Right now, that one isn't maintained anymore, and the other exciting backend, the Scala.js project, operates way earlier in the chain because it has very different optimization needs. And if you're interested actually in generating JavaScript, you should check it out. They're going 1.0 next year. It's made amazing progress. So anyway, back to my Java VM reality here. We use ASM like all the other JVM languages, and the optimizer deals directly with bytecode. And our focus is to get a better inliner, because that's one of the key things that you need in a functional programming language. The JIT only can fix up so much of the indirections that you create. And thanks to the lambdification, closure elimination actually becomes a lot simpler. So in general, you can think of this as eliminating boxing. So putting generating closure is a kind of boxing going between primitives and reference types. We have value classes, for example, which try to solve some of the same problems at the language level to avoid boxing stuff. Tuples, which hopefully on a future JVM version we can return multiple values without putting them in a tuple, but for now that requires inlining them first and then removing the tupling. So this is kind of the earlier. This is in an early phase. This project for the backend here, and it's to use default methods for traits. So we'd like to compile Scala traits directly to interfaces, and we've been experimenting with that. You can check out Lucas's repository if you'd like to see some examples of how that would work. But right now we're just thinking about how we can do that, and we're very interested in doing this because one of the key problems with binary compatibility in Scala is that the way that we compile sources is so different. The binary representation of compiled sources is so different that people are used to think about, oh, the source changes were small, so the binary changes will be small as well. And that's true in Java in general, but it's not true in Scala. And with default methods, we're hoping that will become a little truer. And that will have a large impact on similarly as it has in Java to let us evolve traits more easily. So to give you a sense of the challenges there, traits in Scala can have fields, but those are pretty simple to deal with. You encode them as getters and setters. Of course, you need to deal with initialization, but there are multiple ways you could do that. Even going to something like invoke dynamic to have some kind of lazy initialization semantics that's only done once very cheaply. And the other key thing is that linearization, which does, when you mix in a bunch of traits, you need to know where your supercall goes in each of these traits, and you only know that once you mix in all those traits into a class. So you need to set up your whole hierarchy separately, because of course we do separate compilation. So you need a bunch of super accessors and strategic overrides, let's say, when you're doing default methods to make sure that you can rewire your super, because you only know which way that whole chain will go once you have all those traits together and ready to be mixed into a class. So it looks like I talked really quickly, and I apologize, but that means we have plenty of time for questions. I'd be happy to answer any and all you have, but thanks very much for your attention. And hope to see you at Scala Days, maybe in San Francisco or Amsterdam. Thank you. Yep, question back there.
Is this capturing of this outer variable also related to serialization of functions or something like that, or not?
Yeah, so the question is about the relationship between serialization of closures and capturing the environment, and specifically the outer pointer here. So there's this work by Heather Miller about spores, which are a restricted kind of closure that you can actually ship to your data because it doesn't capture anything in the environment that you don't let it. And so that's kind of something that we're doing outside of the language with macros, which analyze which parts of the environment you capture, and they control that so that they can do that, and that's obviously motivated by the work at Spark. Yep.
What is the impact on debugging when you compile closures in the Java 8 style instead? Sometimes it's been a bit difficult to debug things with explicit anonymous classes.
Yeah, good question. So. And in general, that's a challenge for us to compile to good bytecode also for debugability. So specifically, when using an invoke dynamic, I honestly have no idea how debuggers will deal with that. I think that's going to be a universal challenge, both for Java, like straight Java debuggers, and debuggers that actually are dealing with bytecode that was generated by us. We have a pretty smart debugger in the Eclipse plugin that knows about how functions are compiled, and it'll show you the stack trace a little bit differently, and it'll let you step through each body of the function you pass to a for each, rather than going through the whole for each logic every time, for example. But that's a very interesting challenge, and I think that's something that we're going to see soon, I hope, in the Java world as well, is how do you debug functional programs? Because you're so focused on expressions, line breakpoints, for example, are not as interesting anymore. You want to see where the sub-expression was computed. So there are a whole bunch of challenges with debugging functional programs, and I think part of that goes again back to code style. Like if something is a piece of code that you should be debugging, maybe you should put it in a method rather than in the middle of an expression somewhere. But of course, we don't have perfect foresight, so we don't always know that, and hopefully the tools will get better to help us deal with that. But to summarize, I think we'll benefit from the work that's going to be done in the Java world, the functional Java world. Yep.
The experimental backend, the new style backend with ASM, what are the main problems? Can I just compile my sources with it, or do I have to compile all libraries with it?
No, so the question is about the experimental backend in 2.11. It's completely a drop-in replacement, so it's designed to generate binary compatible code with the standard backend, and we test that, but we can't really guarantee that. So as in general, you shouldn't publish artifacts compiled with the experimental flags to Maven, but if you want to use it on your own machine, you can just do it and use all the artifacts that are already out there. It's actually, the backend itself has been in there for a while. We're mostly working on the optimizer now and the Java 8 specific parts of the backend. Well, I'll be here all week in case you'd rather ask me in person. Thanks again. Have a good conference.